Thank you very much for the introduction. Yeah, this is joint work with my supervisor, Katrin Welka, and PhD student Tim Suhan. Here we wanted to derive a novel shape space, which enables us to, optimize piecewise smooth shapes. And for defining this novel shape space, there are different topics, different tools that we need to connect to define the shape space, which I will give an introduction on in the first part. And then we will look at the definition of this shape space and also derive an optimization technique, which we will apply to an optimization problem constrained by the Navier-Stokes flow. So, starting with the introduction. Well, as I said, there are these different topics that we need to consider when defining our shape space, which are shape optimization on Riemannian manifolds. We have the topic of piecewise smooth shapes, and also very important, the optimization of multiple shapes. Well, start with the shape optimization on Riemannian manifolds. What is shape optimization? Just a simple explanation. During the optimization process, an ellipse could turn into a circle. And shape optimization is widely used in application, for example, in aircraft design, also in medical applications for the design of cardiac stents, and also in fluid mechanical problems, which will be our example, which we will see later in the applications. So just a general introduction, but we will look more into detailed into the definition of a shape optimization problem, which looks as follows. So we have a shape functional j, which may be constrained, so it may depend on some state function y, constrained by some differential operator with boundary conditions. And here in the definition, what is a really crucial part is the shape space U. So the space where shapes live, which we optimize the shape functional. Okay, so we'll look a little bit more into this. So what is a shape space is so far just an abstract space where elements live. So, in the figure, just visualization. So each shape, we have U1, U2, it can be an ellipse, it can be a star. And we want to optimize. So we want to maybe use the gradient descent algorithm, Newton method, whatever. But first, important is that we need to somehow measure distances between shapes. So that's why Riemannian manifolds are suitable for to choose as a shape space. Okay. Now we consider our shape space to be a Riemannian shape space. So we're with the metric G. Then we have the notion of Riemannian shape gradient. Well, the definition is just the usual definition for a gradient for a function between two smooth manifolds, using the metric and the push forward of our shape functional J, which is in this case our function. Okay. And I already mentioned that solution techniques for shape optimization problems, we often use gradient method. So, we talked about shape spaces and how we want them to look like, and now we want to look into two examples for suitable shape spaces. It is quite maybe a bit similar to some shape spaces we already seen. We have the shape space of simple closed curves and the shape space of simple open curves. You can find, for example, in the book Manifolds of Differential Mappings by Peter Michor, but there are many works of Peter Michor and Mumford on these shape spaces, and they examine the different metrics on these shape spaces. Okay, so far on an introduction to shape optimization on Riemannian manifolds, and the other important topic here are the piecewise smooth shapes. Well, piecewise smooth shape, for example, are U depicted here in the picture, a star. And obviously, if we look back at the examples we have just seen, this U is not an element in the space B. Well, it's obviously not smooth. And the motivation why it is important for us to consider these well, maybe star is not the best example in an application, but still a non-smooth shapes, is because they are often counted as an optimal shape in fluid mechanical problems. And yeah, and this is it's similar, but these are two different things that we want. For one, we want to allow initial shapes to be non-smooth, piecewise smooth, and the other part is that we want our shapes, which may have been smooth in the beginning, to develop kinks during the course of the optimization. But we will, I will say something on these two different things later. Okay. So far on the piecewise smooth shapes, and now on the optimization of multiple shapes. Well, here I refer to the paper PDE constrained shape optimization towards product shape spaces and stochastic models by my supervisor and other authors. And from this I want to give here some basic definitions, which we will refer to later on. Okay, we have a product shape space, which means that we have a manifold UN, which is a product of n manifolds, and we have our product metric G, defined by the pullbacks of the canonical projections as usual. And so first, well, analogous to the shape functional that we have seen in the definition for shape optimization problem, we have a multi-shape functional J, and we have the multi-shape gradient, again analogously to the, well, one-dimensional case where we don't have a product shape space. Okay. So far on this introduction, and what is our aim? We want to be able to like have a shape space which enables us to optimize multiple shapes, which may be smooth or maybe non-smooth. So for this, our aim was to define a novel shape space, which I will introduce now. Okay, and but before I give the formal definition of a new shape space, I will explain it using an example, the one we already seen, the shapes U1 and U2. Oh, just a second. U1 and U2. U1 obviously non-smooth, U2 a smooth ellipse. Okay, so let's set our spaces, manifolds UL, to be the space of simple open curves for the indices L from 1 to 12. And U13 we set to be the shape space of simple closed curves. This way, well, if you look at U1, you see that, well, it's just 12 straight lines. And a straight line is a smooth shape, smooth open shape. So we can say that U1 is an element of the product of the first 12 shape spaces, and U2 in the last. So what do we want? We want to define a shape space, some abstract name M, such that we have a Riemannian structure, and such that the multi-shape U, which consists of our shapes U1 and U2, is an element of this shape space. Now on the formal definition here, again, UI Riemannian manifolds, product shape space UN, and well, here the formal definition. We call it the S-dimensional shape space of piecewise smooth shapes on UN. And basically what this definition means is that an element in MS of UN is a group of S shapes, and each of these S shapes, UJ, is an element in the product space of NJ smooth manifolds. Well, that's all this definition says. So, well, the main idea here is to take a non-smooth shape and pull it into its smooth pieces and bringing them together. And then we want a clean mathematical definition. So in this shape, the multi-shape U always consists of S individual shapes. Okay. So we have the definition of the shape space. Now we still want to know how to get an optimization technique on the shape space. So and in our case, we want the gradient descent algorithm on MS of UNs to solve this kind of shape optimization problem. And for this, we need to look some more into the structure of a novel shape space. In the first part, in the tangent space, so any element in our shape space, it corresponds to just an element in our initial shape space UN. So any element U1 to US corresponds to an element U tilde 1 to U tilde N. So we just set the tangent space of a novel shape space at some point, at some shape U, to be equal to the tangent space of the shape space U and U tilde. And analogously we do with the metric, the action of the metric. Remember the definition or the construct of the multi-shape, multi-push forward, multi-shape gradient, which we have seen for the optimization of multiple shapes. We can easily adjust them to our new shape space. And the last thing we need to consider is the multi-exponential map, which again, we use the exponential maps on the individual manifolds we consider. Okay. So now with this, we are able to define an optimization algorithm, a gradient, as I said, a gradient descent algorithm on n mass of un with the metric Gn. We have the following. We have our initial shape. We have a constant for the break condition. We also, here it's like quite abstract, but depending on how we compute the step size, we also need constants for the computation of the step size. And while loop, so for the break condition in each step, in each iteration step, we compute the multi-shape gradient V with respect to our Riemannian metric, and we compute step size alpha. Well, in some way, we usually use a major backtracking, and we use the multi-exponential map to get the next iterate shape. Well, in the picture you can maybe see how we use this exponential map for our optimization algorithm. Okay, good. So we have so we have our novel shape space, we have our optimization technique, and we have to keep in mind that all this theoretical part that we do it to apply it to some, let's say, real life applications. Well, they're not always like that in real life, but we need to make some adjustments to our shape space, especially to the choice of initial shapes, so that it is useful for us in the optimization algorithm. So we define two rules for the choice of initial shapes. The first rule, it may be clear because as I introduced the shape, the star-shaped U1, that we want to consider closed shapes for our algorithms. So whenever we have some shape from U1 to US, some Uj, which is constructed as the product of multiple shapes, nj shapes, well, this is just an abstract rule. What this just means is that these pieces that we get from the individual shape spaces, they are glued together at their ends. So we get closed shapes. And the second rule is, and this is what I mentioned before, is that for applications where the development of kinks and shapes is wanted, is desired, then whenever we have an initial smooth shape, for example a circle, we approximate it with elements in for example, in the shape of the shape space, with elements in the shape space of open curves. Just a simple example, it wouldn't be so good for the optimization, but just to make clear what I mean, if we have a circle, we can just approximate it with n straight lines or something. That wouldn't be quite good for the algorithm, but yeah, just to explain the second rule. Okay, so we have our shape space, we have our optimization technique, we have these rules, and now we come to the last part, to the application of this newly defined shape space to an optimization problem. Model formulation. The problem is the following. So the shape functional is given by the viscous energy dissipation which we want to minimize with the Frobenius product and the integral of some state V. V here is, well, from the state Y, Vp, V is the velocity and P the pressure, constrained by the Navier-Stokes equation. So we want to look at a fluid mechanical problem. And then we set material constant mu and rho, viscosity and density, and the domain we consider is the unit square. That's something we often use with our already often seen initial shapes U1 and U2, so our non-smooth shape and our smooth shape. Now on to some numerical results. We get the following. Okay, oh, oops, sorry. Okay, so what do we see here? On the model, we have depicted in these pictures the fluid velocity magnitude, and we have an inflow on the left boundary for this model, and we have obstacles for this this fluid given by our two shapes. And what we want to do, well, we want to minimize it. So we see in the first picture that the velocity is quite high with the initial shapes, and then converges. Yeah, we also have boundary conditions here, but yeah. And you see in each for each picture, you see the value of the objective function. And you may, well, it's obviously that the optimized shapes have a given decrease value of the objective function. You may wonder why it's higher in D than it goes up from C to D, but we also have to consider the that the optimal shapes, they fulfill the geometrical constraints, while the one in C does not yet. Yeah. Okay, so these are numerical results. Maybe a quick summary. What we have done, we have defined a novel shape space, which we called MS-FUN, which has the properties of it has a Riemannian structure. We get a Riemannian metric, and we can make use of classical optimization algorithms, like in our case the gradient descent algorithm, which we have derived on a novel shape space, and we can apply this optimization algorithm well, to find optimal shapes for the minimization of the viscous energy dissipation constrained by Navier-Stokes. And that's it from me. Thank you for the attention.
Thank you. Do we have any questions?
Thank you for your talk. In your application, do you constrain your shapes to keep the same area, or
to keep the same
to be of the same area all the time when you optimize the shape, or area?
Ah, okay. Yes, yes,
yes.
That's what you usually do in the.
Otherwise, will disappear.
Yeah.
Very small question also on the application. Then, so in practice, the shape that minimized, they have kinks, like in practice.
Not in all. In general, in fluid mechanical problems, it is often the case. I mean, I'm not an engineer, so I don't want to say something wrong, but I would say it's not, you can say that it's always the case. And for other problems, it may be different. Like, no.
All right. Okay.
Yeah.
Thanks.
Any other questions? No? If not, then let's thank the speaker again. This was all for our geometrical learning session.
Let me just thank you very much for attending this session. Yeah, I forgot to say that this session was organized also in cooperation with Guillaume Charpia, who could not come for good reasons. So I'm very glad that we had a bit of frugal machine learning and also some geometry. So I wanted to have both in my session, and I hope that's a fruitful combination. Thank you very much. Have a nice lunch and enjoy the rest of the conference.